The Water Staircase. How the Panama Canal Defies Physics. Chapter 1. The Mountain Between Two Oceans. Every time you buy something shipped from Asia, a phone, a piece of furniture, a pair of shoes, there is a reasonable chance it crossed a mountain to get to you, carried not by truck or train, but by a ship. A vessel the length of 3 football fields, weighing 100,000 tons, was lifted 26 meters into the air by water alone, carried over the Continental Divide of the Americas, and lowered back down to sea level on the other side, without a single pump, without a crane, without anything more sophisticated than gravity and a set of steel gates. This happens between 30 and 40 times every day. It has been happening since 1914. The Panama Canal is the reason the modern global economy works the way it does. Without it, every container ship traveling between Asia and the American East Coast would add roughly 2 weeks and 15,000 kilometers to its journey, going around the southern tip of South America. Every tanker, every bulk carrier, every ship carrying the goods that fill the stores you shop in would face the same detour. The canal is not a convenience. It is load-bearing infrastructure for the global economy, and almost nobody who depends on it has any idea how it actually works, or how close it came to never existing at all. How does a 100,000-ton ship climb a mountain using nothing but water? Why did the most celebrated engineer of the 19th century try to build this canal and kill 20,000 people in the attempt? And what does a drought in Panama have to do with the price of everything you buy? Those are the questions this video answers, and the answers are stranger and more unsettling than most people expect. To understand why the canal works the way it does, you have to start with the man who tried to build it the wrong way, and understand exactly why his approach failed, because the failure is the reason the canal was built the way it was. Ferdinand de Lesseps was not an engineer. He was a diplomat and a promoter, and by 1879, the most celebrated infrastructure builder in the world. A decade earlier, he had pushed through the construction of the Suez Canal, the waterway connecting the Mediterranean and the Red Sea that cut the shipping route between Europe and Asia by thousands of miles and reshaped global trade. When the Suez Canal opened in 1869, de Lesseps became a national hero. Emperors received him. France celebrated him. And when he announced in 1879 that he intended to build a second canal, this one across the Isthmus of Panama, connecting the Atlantic and Pacific Oceans, the world believed him. More than 800,000 private investors in France poured over £1 billion into his company. The plan was straightforward. Dig a canal at sea level across Panama, exactly as had been done at Suez. No locks, no elevation changes, no complicated water management, just a channel cut through the isthmus at the level of the ocean, letting ships sail through as if crossing a wide river. Panama is not Egypt. The Suez Canal works because the terrain between the Mediterranean and the Red Sea is flat desert, sitting almost exactly at sea level. Digging a channel through it meant moving sand. Panama is a rugged spine of mountains and jungle, sitting on volcanic rock and unstable clay, crossed by rivers that flood with a violence that has no equivalent in the Egyptian desert. The central section of the isthmus, the Continental Divide, rises to hundreds of meters above sea level. A sea-level canal through it would require removing more earth than any construction project in human history, through terrain that was constantly trying to put the earth back. De Lesseps visited Panama in January 1880, during the dry season when the jungle was relatively peaceful and the rivers ran low. He spent a few weeks, declared the project feasible, returned to France, and began spending the investors' money. He did not return to Panama during the rainy season. Construction began in 1881. Rain fell in quantities that European engineers had never encountered, up to 3 meters per year in the construction zone. The Chagres River, which crossed the proposed canal route, could rise 9 meters overnight during heavy rain, turning from a navigable waterway into a wall of water that destroyed everything in its path. The volcanic clay hillsides that workers excavated during one shift would liquefy in the next rainstorm and slide back into the trench. David McCullough, in his History of the Canal, The Path Between the Seas, documented how crews at the Culebra Cut, the central mountain section, would sometimes arrive in the morning to find the previous day's work completely buried. The mountain was refilling the hole faster than they could dig it. The mountain was not what killed the project. What killed it was invisible, and it bred in the standing water that pooled everywhere in the jungle after rain. Malaria and yellow fever had existed in Panama for centuries. The construction project, tens of thousands of workers brought in from the Caribbean, Europe, and elsewhere, most with no immunity to tropical diseases, turned the canal zone into one of the most lethal places on Earth. Workers who arrived healthy were often dead within weeks. The company's administrators, frightened of alarming the investors in Paris, systematically hid the death toll. Letters were censored. Mortality statistics were falsified. The true number of deaths during the French construction period is still debated, but estimates converge around 20,000 to 22,000 dead over 8 years. Engineers, laborers, doctors, administrators, in a project that was supposed to connect 2 oceans and instead filled a jungle with graves. The company ran out of money in 1889. The French government investigated. De Lesseps and his son were charged with fraud. The old man, by then in his mid-80s, was convicted but never imprisoned. He died in 1894, still insisting the canal could be finished. His company left behind 1 billion francs of debt, the ruined savings of hundreds of thousands of French families, a half-finished trench in the jungle, and a lesson that the next generation of engineers would have to decide whether to learn. For years after the French collapse, a Panama Canal seemed finished as an idea. When the United States began seriously considering a canal across Central America in the late 1890s, the Panama route was far from the obvious choice. A route through Nicaragua, flatter terrain, existing lakes that could be incorporated into the design, no legacy of catastrophic failure, was seriously favored in Congress. Nicaragua came very close to being chosen. What changed the outcome was a combination of engineering analysis and an unlikely piece of evidence, a Nicaraguan postage stamp featuring a volcano. A lobbyist for the Panama route distributed the stamp to senators on the Canal Committee as a subtle reminder that Nicaragua sat in an active volcanic zone. The argument, combined with a serious engineering assessment showing that the Panama route was shorter and more direct despite the terrain challenges, eventually swung the vote. In 1903, the United States secured rights to build a canal through Panama. In 1904, construction began. The Americans arrived with more money, more machinery, and a fundamentally different approach to the central problem. The chief engineer, John Stevens, who took over in 1905, spent his first months not designing anything but understanding what the French failure actually meant. His conclusion was direct. A sea-level canal through the Continental Divide was not achievable. The mountain could not be removed, but it could be bypassed. Stevens's solution was to flood the valley of the Chagres River running along the base of the mountain range. Build a dam across the Chagres, create an enormous artificial lake at 26 meters above sea level, and use that lake as the crossing point. Ships would be lifted from sea level to the lake on one side, cross it as if it were a bridge between oceans, and be lowered back down on the other. The lifting and lowering would happen in water-filled chambers, locks, operating entirely on gravity. The water that had been the French project's enemy would become the engine of the American one. Before the first lock could be designed, or the first stone of the dam laid, though, the Americans faced exactly the same enemy that had destroyed the French project. The jungle was still there. The clay was still unstable. The mosquitoes were still breeding in every pool of standing water between the two coasts. The difference was that by 1904, medicine had something the French had lacked: a theory about where yellow fever and malaria actually came from. Whether that theory would be believed, funded, and acted on in time was not an engineering question. It was a political one, and it very nearly went the wrong way. Chapter 2. How America Built What France Could Not. In 1904, a U.S. Army doctor named William Gorgas arrived in Panama with a theory that most of his superiors considered a distraction and a budget that was nowhere near what he said he needed. The theory was that malaria and yellow fever were not caused by bad air or swamp gases, the prevailing medical view of the era, but by specific species of mosquitoes. The implication was that both diseases could be controlled not by treating the sick after infection, but by eliminating the mosquitoes before they could bite. Gorgas had already tested this approach in Havana after the Spanish-American War, where a targeted mosquito eradication campaign had essentially eliminated yellow fever from the city within months. He believed the same could be done in Panama. His superiors in Washington believed the money would be better spent on excavation equipment. The argument that followed was not a minor bureaucratic dispute. It was a question about whether the American Canal project would repeat the French one. Gorgas spent the better part of his first year in Panama fighting for resources while yellow fever cases among the new American workforce began to climb. The Canal Zone's chief sanitary inspector resigned in frustration. Several senior American engineers contracted the disease. The parallels with the early French period were close enough to alarm anyone paying attention. What finally broke the impasse was a yellow fever death that could not be ignored politically. The chief engineer of the canal project himself fell ill, survived, but was shaken enough that the case for Gorgas's program became impossible to dismiss. By 1905, Gorgas had the funding and authority he needed. What he did with it was systematic to a degree that had no real precedent in public health. The Aedes aegypti mosquito that carries yellow fever breeds exclusively in standing fresh water. Any container, any puddle, any water barrel left uncovered. Gorgas sent crews through every building in Colón and Panama City, draining containers, pouring a thin film of oil on any water surface that could not be drained to suffocate mosquito larvae, screening every window and door of every structure housing workers, and fumigating every room in every building from the top floor down. At its peak, Gorgas had over 4,000 workers dedicated solely to sanitation and mosquito control. Yellow fever, which had killed hundreds of workers per year during the French period, was essentially eliminated from the Canal Zone by 1906, 2 years after Gorgas arrived. Malaria took longer, but infection rates fell by more than 90% before the canal opened. The death rate among canal workers dropped to roughly 6 per 1,000 per year, lower than the death rate in many American cities at the time. With the disease problem under control, the actual construction could begin in earnest. And the central challenge, the Culebra Cut, was waiting. The Culebra Cut was the 9-mile stretch of mountain at the center of the isthmus, where the Continental Divide crossed the canal route. The French had started excavating it and removed some material, but the combination of landslides, equipment failures, and disease had prevented anything close to the progress needed. When the Americans assessed what remained, the numbers were daunting. The cut needed to reach a navigable depth at a point where the mountain rose more than 100 meters above the required channel floor. The American approach was defined first by scale. At the height of construction, more than 100 steam shovels worked simultaneously in the cut, each capable of moving several hundred tons of material per day. A dedicated railroad system, hundreds of dirt cars on tracks that were constantly repositioned as the excavation advanced, carried the removed material away continuously. At the peak of the project, the canal construction employed over 40,000 workers, making it one of the largest labor operations in American history to that point. The second defining decision was about the slopes themselves. The French had tried to cut straight vertical walls through the clay hillsides, which had failed repeatedly because the clay became liquid under heavy rainfall and slid back into the trench. The Americans cut the slopes in stepped terraces rather than vertical faces, reducing the pressure on the unstable material and making the slides smaller and more manageable. It did not eliminate the landslides. Nothing could, but it reduced them from project-ending events to manageable setbacks. In 1913, with the canal nearly complete, a major slide partially refilled sections that had taken months to excavate. The engineers widened the cut further and accepted that some sections would require ongoing dredging indefinitely. The mountain was participating in the project on its own terms, and the Americans had learned enough from the French experience to work around that fact, rather than pretend otherwise. While the Culebra Cut was being excavated, the other half of Stevens's plan was taking shape at the mouth of the Chagres River on the Atlantic side. The Gatun Dam was under construction. The logic of the dam was inseparable from the logic of the entire canal design. The Chagres River had been one of the primary enemies of the French construction effort. Its floods had repeatedly destroyed work and threatened workers. The American solution was to absorb the river entirely, build a dam large enough to turn the whole Chagres Valley into a reservoir, creating a lake whose surface sat 26 meters above sea level. The lake would serve as the canal's central crossing, its water supply for the locks, and its flood control system all at once. The river that had plagued the French became the foundation of the American design. When the Gatun Dam was completed in 1913, it was the largest earth dam in the world. The lake behind it covered over 400 square kilometers and was the largest artificial body of water on Earth at the time. Dozens of villages were submerged. The original course of the Chagres River disappeared under the rising water. Some of the material excavated from the Culebra Cut was used to build the dam's earthwork core, creating a direct material connection between the two greatest engineering challenges of the project. The mountain that had to be cut through and the river that had to be contained were, in the end, helping solve each other. The canal opened on August 15, 1914, when the cargo ship Ancon made the first official transit. The timing was unfortunate. The assassination of Archduke Franz Ferdinand had occurred 10 weeks earlier, and by August, the First World War was fully underway. The canal that had taken a decade and $375 million to build opened to minimal international attention. But it worked. Ships entered on one side, rose through the locks to the lake, crossed the lake, descended through the locks on the other side, and emerged into a different ocean. The water staircase that Stevens had sketched on a drawing board in 1905 was moving real vessels between real oceans, and the system at the heart of it, the lock chambers that lifted and lowered ships using nothing but gravity and flowing water, had been operating exactly as designed from the first day. Understanding how that system actually works and why it places a demand on Panama's fresh water supply that no amount of engineering can fully resolve is where this story goes next. Chapter 3. The Water Elevator Picture. A bathtub the size of 3 football fields. Fill it with enough water to supply a city of 50,000 people for a day. Do it in 8 minutes, using no pumps, no electricity for the water movement itself, no external power source of any kind. Just the weight of water sitting higher than where it needs to go. This is what happens every time a ship passes through a lock at the Panama Canal. And the fact that it works, that it has worked reliably over 100 million times since 1914, comes down to a physical principle so simple it is taught to children, and an engineering implementation so precise that the tolerances are measured in centimeters on structures weighing hundreds of thousands of tons. The basic principle of a canal lock is older than Panama by several centuries. Locks were used to move boats up and down hills in European waterways as far back as the 15th century. Create a chamber with gates at both ends, fill it with water to raise a vessel, or drain it to lower one. Then open the appropriate gate to let the vessel proceed. What the Panama Canal did was apply this principle at a scale that had never been attempted before, in conditions that created engineering problems the scale itself generated. A ship entering from the Atlantic side reaches the Gatun locks first, 3 chambers in sequence, each raising the ship approximately 8.5 meters. By the time the vessel exits the 3rd chamber, it sits 26 meters above the ocean it just left, floating on the surface of Lake Gatun. On the Pacific side, the process runs in reverse. The Pedro Miguel locks lower the ship about 9 meters to a small intermediate lake, and then the Miraflores locks, 2 chambers, bring it the remaining distance to Pacific sea level. The full transit covers about 80 kilometers and takes between 8 and 10 hours under normal conditions. The filling and emptying of each chamber happens through a network of culverts, large tunnels running through the walls and floors of the lock structure. Each main culvert is roughly 6 meters in diameter. These tunnels connect the chambers to each other and to Lake Gatun through a branching system of smaller openings in the chamber floor. When a chamber needs to be filled, valves open and water from the higher source, the adjacent upper chamber or the lake itself, flows downward through the tunnels and rises through the floor of the lower chamber, lifting the ship inside. When the chamber needs to be emptied, the valves open in the lower direction and the water drains away. The volume involved in a single filling cycle is approximately 197 million liters, enough to fill around 79 Olympic swimming pools. It moves in 8 minutes. The distribution of this inflow through dozens of floor openings keeps the water rising smoothly rather than as a turbulent rush, so the ship lifts steadily without being pushed against the walls. No electricity powers the water movement. The entire filling and emptying process runs on gravity alone. This was a reliability decision as much as a cost decision. A gravity-fed system has no pumps to burn out, no motors to fail, no power supply to be cut. The water moves because water at a higher elevation has energy that it releases when given a path downward. The lock operators control this by opening and closing the culvert valves, but the energy that lifts the ships comes from the lake, and ultimately from the rainfall that fills it. The ships move through the chambers at under 3 kilometers per hour and are guided by electric locomotives running on toothed rails along the lock walls. These are called mules, a name inherited from the actual draft animals that performed this function on earlier canal designs. They attach to the ship via heavy steel cables from bow and stern, 4 per side on a large vessel. Their job is not to propel the ship forward, but to keep it centered in the chamber. The clearance between the side of a Panamax vessel and the lock wall is 60 centimeters on each side, roughly the width of a person's shoulders, and at slow speeds in a confined space, even small lateral movements can bring a 100,000-ton hull into contact with a concrete wall. The mules provide continuous corrective tension to prevent this. Every vessel transiting the canal, regardless of the experience of its own captain, takes on a Panama Canal pilot at the approach anchorage. The pilot assumes navigational authority for the transit and coordinates with the mule operators, the lock control rooms, and the canal traffic management system. Canal pilots train for years and must demonstrate proficiency in handling every class of vessel that uses the waterway. The canal has operated since 1914 without a single accident that blocked transit for more than a few hours, a record that reflects both the physical design and the training of the people running it. The lock gates themselves are worth examining closely because their design contains the principle that has allowed them to function for over a century under conditions that would destroy a less carefully considered structure. Each gate consists of 2 leaves, hinged at the walls and meeting in the center of the channel when closed. The leaves close at an angle, forming a shallow V-shape with the point directed upstream, toward the higher water pressure. When water pushes against this angled surface from the high side, the force splits into 2 components, one pushing the gate downstream and one pushing the 2 leaves toward each other and into the gate sill. The gate seals itself. The harder the water pushes, the tighter the closure becomes. Each gate leaf is also hollow and watertight, which makes it partially buoyant. A 700-ton structure that floats slightly in the water it is retaining requires far less hinge capacity than a solid plate of the same mass. To open the gate, the lock operators first equalize the water level on both sides using the culvert system, removing the pressure differential. With pressure equal on both sides, the leaves swing open with minimal effort. The sequence is always hydraulic equalization first, then mechanical opening, and the control systems enforce this sequence because a gate opened against a large pressure differential would damage the operating machinery. The lock system is elegant, reliable, and has functioned continuously for over a century. It is also consuming something irreplaceable every time it operates. Each transit drains approximately 197 million liters of fresh water from Lake Gatun into the ocean, water that does not return. With 30 to 40 ships transiting daily, the canal uses billions of liters of fresh water every day, all of it supplied by rainfall on the Panamanian watershed. In a normal year, the rain is sufficient. In 2023, it was not, and what followed showed the world exactly how much depends on weather patterns over a small patch of Central American jungle. Chapter 4. The Drought That Stopped the World. In October 2023, a queue of ships waiting to transit the Panama Canal stretched to 130 vessels. The waiting time had grown from the normal few hours to nearly 3 weeks. Container ships, liquefied natural gas tankers, bulk carriers loaded with grain, all of them sitting at anchor in the approaches to the canal, burning fuel and accumulating costs while waiting for a transit slot that the canal administration could not guarantee. The annual transit capacity had been cut from roughly 14,000 ships to under 9,000. Shipping companies were calculating losses in hundreds of millions of dollars per month. The cause was not a mechanical failure, not a political crisis, not a labor dispute. The cause was that it had not rained enough. The El Niño weather pattern that developed in 2023 reduced rainfall across Central America significantly below historical averages. Lake Gatun, which supplies every lock transit with fresh water and also provides drinking water for approximately 2.5 million people in Panama City and Colón, fell to levels not recorded in decades. When the lake drops below a certain threshold, the canal administration has no choice but to restrict traffic. There is simply not enough water to fill the lock chambers at the rate needed to sustain normal operations. The specific restriction imposed was on draft, the depth to which a ship's hull extends below the waterline. Under normal conditions, the canal allows vessels with a maximum draft of approximately 15.5 meters. At the peak of the drought, this was reduced to 13 meters. For a large container ship, that difference means leaving 10 to 15% of cargo capacity empty at the loading port. Ships that had been contracted to carry specific quantities could not carry them. Shippers either found alternative routes, adding weeks of additional transit time around Cape Horn, or left cargo behind and made additional voyages. Neither option was economically acceptable, and neither was available at short notice without significant cost. The disruption spread rapidly through global shipping. Container ships rerouted to the Suez Canal, adding weeks and thousands of miles. Liquefied natural gas tankers that relied on the Panama route booked the longer southern route. Bulk carriers carrying grain and coal paid premium prices for transit slots or accepted partial loads. The insurance and logistics firm Allianz Trade estimated that the restrictions were adding approximately $500,000 in additional costs to a typical container ship rerouted via Suez. Multiplied across the thousands of affected ships, the disruption was costing the global industry billions of dollars, all traceable back to a rainfall deficit over a watershed the size of a medium-sized American county. The deeper problem the drought exposed had been understood by engineers and hydrologists for decades. The Panama Canal's water supply comes entirely from rainfall in the Chagres River watershed. There is no alternative source, no other river, no groundwater system, no desalination capacity that could substitute for the lake if the rainfall fails. The canal is a rain-powered machine, and when the rain fails, everything that depends on it fails with it. The volume of water consumed by lock operations makes the dependency acute. Each ship transit through the original locks uses approximately 197 million liters of fresh water. With 30 to 40 ships per day, the daily consumption reaches several billion liters, all of it draining from the lake into the ocean, unrecoverable. The lake is replenished only by rainfall, and in normal years the rainfall exceeds the consumption. In drought years, the arithmetic runs the other way, and the canal has no reserve mechanism beyond the lake itself. The 2023 drought was not the first time the canal had faced water constraints, but it was the most severe in recent history, and it arrived when global shipping was already under pressure. The timing amplified the economic impact. Ships that could not get through Panama in reasonable time diverted to alternative routes, pushing freight rates higher across the entire system. A hydrological problem in one watershed in Central America produced measurable effects on the cost of goods in Europe, energy prices in Asia, and food distribution in North America. The structural issue runs deeper than any single drought year. Climate models consistently project that El Niño events will become more frequent and more intense as global temperatures rise. The Chagres watershed has also been under pressure from deforestation and agricultural development for decades. A study published in the journal Ambio in 2018 documented ongoing forest loss within the canal watershed and projected that continued land use change would reduce the water yield of the Chagres catchment over the coming decades, compounding the effects of future drought years. The most straightforward response to the water supply vulnerability is additional reservoir capacity. A dam on the Indio River, a tributary of the Chagres, had been studied and designed for years. The project would create a reservoir capable of supplementing Lake Gatun's supply during dry periods. Its cost was estimated at around $1 billion, modest relative to the economic value of the canal and the losses caused by the 2023 restrictions alone. Construction had been blocked by a Panamanian law restricting development within the canal watershed. In 2024, Panama's Supreme Court struck down the provisions blocking the reservoir. Construction had not yet begun at the time this research was conducted. The 2023 drought made visible something that had always been true about the Panama Canal. Beneath the locks and the dam and the artificial lake, the whole system rests on rainfall. The miter gates seal under pressure. The culverts fill by gravity. The mules keep the ships centered. All of it works as long as the water is there. When the rain stops, none of the rest of it matters. And in a world where the rain is becoming less predictable, that dependency is the central vulnerability of the most important waterway on Earth. Addressing it was the challenge that defined the canal's first major infrastructure investment of the 21st century, an expansion that would cost more than $5 billion and change what ships could use the canal, while introducing a new approach to the water consumption problem that the original designers had no way to solve. Chapter 5. The $5.25 billion upgrade. By the early 2000s, the Panama Canal was approaching a ceiling its original designers could not have anticipated. The Panamax vessel, the largest ship that could fit through the original lock chambers, had become the de facto standard for a generation of container shipping. But the economics of the industry were pushing toward larger vessels that the original locks could not accommodate. The biggest container ships being ordered were carrying 12,000, 15,000 containers. The Panamax maximum was around 5,000. These new ships were too wide, too long, and too deep for the original chambers, and they were being routed around Panama entirely, through Suez or around Cape Horn. If the trend continued, the canal would gradually become a route for medium-sized vessels, while the most valuable cargo moved on other paths. The economic stakes for Panama were serious. Canal revenues fund a substantial fraction of the national budget. A canal becoming irrelevant to the future of global shipping was a canal whose revenues would stagnate. The expansion proposal that went to a national referendum in October 2006 involved building an entirely new set of lock complexes alongside the existing ones, with chamber dimensions large enough to accommodate the next generation of container ships. The referendum passed with approximately 78% in favor. Construction began in 2007. The new chambers, 427 meters long and 55 meters wide, compared to the original 305 by 33.5, were large enough to accommodate vessels carrying up to 14,000 containers, roughly 3 times the capacity of a Panamax ship. The project involved excavating tens of millions of cubic meters of material, placing millions of cubic meters of concrete, and fabricating lock gate structures of unprecedented size. It also involved solving the water consumption problem in a way the original designers had understood but could not address with the technology of their era. The water-saving basins are the engineering feature that best illustrates how much had changed since 1914. Each new lock chamber is flanked by 3 large concrete reservoirs positioned at different elevations alongside the chamber. When a ship has been lifted and the chamber needs to be emptied, the water does not drain directly to the lower level or the ocean. It flows first into the highest elevation basin. When that basin is full, remaining water flows to the middle basin, then the lowest. When the next ship arrives and the chamber needs to be filled, the process reverses. Water from the highest basin flows back into the chamber first, supplemented by water from the middle basin, and finally topped off with fresh water from the lake. Approximately 60% of the water that passes through each transit cycle is recycled rather than lost. The practical significance is considerable. A transit through the new locks consumes roughly 114 million liters of fresh water compared to 197 million for the original locks. The expanded canal handles ships 3 times larger while consuming less water per transit. In the context of the water constraints that produced the 2023 crisis, this is the difference between a canal that can sustain traffic through a moderate drought and one that cannot. The new lock gates required a different mechanical approach than the original miter gate design. The chambers were 55 meters wide, too wide for miter gates of manageable size, so the expansion used rolling gates instead, each one sliding horizontally into a recess in the lock wall rather than swinging on hinges. Each rolling gate weighs approximately 4,000 tons and is moved by hydraulic motors. The decision to use a different gate type rather than simply scaling up the original reflected a century of operational experience. The rolling gate configuration handles the lateral loads imposed by large vessels more robustly and requires less precise alignment during installation and maintenance. The project finished in 2016, roughly 9 years after construction began, at a final cost of approximately $5.25 billion. The first commercial transit through the new locks was made by the container ship COSCO Shipping Panama in June 2016. Within months, traffic patterns in global shipping had begun to shift. East Coast ports in the United States that had invested in infrastructure to handle larger vessels saw the traffic increases they had anticipated. The Panama route to the U.S. East Coast from Asia became economically competitive with the Suez route for large vessels for the first time in decades. The expansion did not resolve every challenge the canal faces. The water problem remains. The water-saving basins reduce consumption, but do not eliminate dependence on rainfall, and the original locks continue consuming water at the original rate. The Culebra Cut requires periodic dredging as the unstable slopes continue shedding material. The original infrastructure, now over a century old, demands continuous maintenance investment. But the expansion demonstrated that the fundamental concept, the water staircase, remained as valid in the 21st century as it had been in the 20th, scalable to demands the original designers could not have imagined. What the expansion also did was bring renewed attention to the engineering detail that has kept the lock system working since 1914, the element that the original designers got so precisely right that it has required no fundamental change in over 100 years of continuous operation. It is simpler than any of the technology described in this chapter, and understanding it is the key to understanding why the canal works at all. Chapter 6. The simple genius that holds it all together. Every lock gate in the Panama Canal weighs over 700 tons. Each one stands approximately 25 meters tall. There are dozens of them, arranged in pairs at the entrance and exit of every chamber along both the original and expanded canal. They have been opening and closing under the pressure of millions of tons of water since 1914. The motors that move them are compact electric drives, the kind of machinery you might see in an ordinary industrial facility, unremarkable in scale. The reason these modest motors can move 700-ton gates is not that the motors are powerful. It is that the gates are designed so that at the moment they need to open, they are carrying almost no load at all. This is the engineering principle at the heart of the Panama Canal, the detail that has prevented catastrophe for over 100 years. It is worth explaining carefully because its elegance is not immediately obvious, and because understanding it reveals something important about why the canal has lasted as long as it has. Each lock gate consists of 2 leaves, hinged at the walls and meeting in the center of the channel when closed. The leaves close at an angle, forming a shallow V shape with the point directed upstream toward the higher water. When water pushes against this angled surface from the high side, the force splits into 2 components, one pushing the gate downstream and one pushing the 2 leaves toward each other and into the gate sill. The gate is pressed shut by the water pressure itself. The harder the water pushes, the tighter the seal. A flat gate under the same water pressure would behave differently. The force would act perpendicular to the gate surface, trying to push the gate downstream and pry it open at the center where the 2 leaves meet. The miter geometry converts this destructive force into a sealing force. The same pressure that would eventually work open a flat gate makes a miter gate stronger the more it is applied. The practical consequence is that the mechanical systems holding the gate closed do not need to be designed to resist the full water force. The water is doing the sealing. This means the hinges, the sill seals, and the operating motors only need to handle the weight and inertia of the gate structure itself, not the hydraulic load. Combined with the fact that the gate leaves are hollow and partially buoyant, reducing their effective weight in the water. This is why gates of this size can be moved by motors that would seem undersized for the task. Opening the gate requires one step before the motors run, equalizing the water level on both sides using the culvert system. When the levels are equal, the pressure differential across the gate drops to near zero. The leaves are no longer pressed together by the water, and they swing open with minimal effort. Getting the sequence wrong, attempting to open a gate against a significant pressure differential, would damage or destroy the operating machinery. The control systems prevent this, but the real protection is the geometry. A gate that can only be opened easily when conditions are safe, and that becomes more secure the more dangerous the conditions are on the other side. The miter gate principle dates to 15th century Holland. What the Panama Canal engineers did in 1908 was apply it at a scale it had never been used before, and build the supporting systems, the culvert network, the operating machinery, the backup protections, to match the demands of the environment. They chose a proven principle over a novel one, and the choice has held for over a century. The backup systems protecting the gates from collision follow the same thinking. Heavy chains were originally stretched across the channel floor at each lock entrance, attached to winches on the walls. A vessel moving too fast would press against the chain before reaching the gates, providing a mechanical stop independent of the gate mechanism. The chains were removed in 1980 as impractical given the volume of traffic, but secondary gate leaves remain recessed into the lock walls at each chamber, deployable within minutes if the primary gates are damaged. These secondary gates have never been deployed in a real emergency. They exist because the engineers who designed them understood that a system operating under this much pressure, this many times per day, across this many decades, would eventually face conditions outside normal parameters, and that having a second line of defense cost far less than explaining why one had not been provided. In over 110 years of operation, no lock gate has failed in a way that released water catastrophically. There have been collisions, ships misjudging speed and striking the gates, and some have caused damage requiring repairs and temporary closures. In every case, the gate maintained its seal or was repaired before any breach. The secondary gates have never been tested against a real emergency. This is not luck. It is the consequence of a design philosophy that placed reliability above novelty and built redundancy into a system where failure was not an acceptable outcome. The Panama Canal that opened in 1914 was not the Canal de Lesseps had imagined. It went over the mountain instead of through it, using water to lift ships to a height no engineer of the previous century would have considered practical, and holding that water back with gates that used the pressure of the water itself as the sealing mechanism. The Chagres River, that had flooded and destroyed the French construction effort, became the water source that powered the American design. The mountain that could not be removed became the reason the lake sat high enough to work. The problems the terrain created were folded into the solutions. What the canal cannot do is control the rain. The drought of 2023 made clear that the most sophisticated lock system in the world is ultimately dependent on weather patterns that no structure can replace. The new reservoir on the Indio River, when it is built, will add resilience. The water-saving basins in the expanded locks have already reduced per-transit consumption significantly, but the canal will always be a freshwater machine in a world where fresh water is becoming less predictable. The gates will keep sealing under the pressure of the water behind them. The culverts will keep filling by gravity. The mules will keep centering the ships, and the mountain will keep sitting there, 26 meters above both oceans, exactly as it has since before anyone thought of building a staircase over it. A note from the author. This video required several weeks of research across engineering histories, hydrological studies, canal authority reports, and first-hand accounts of the construction period. The most valuable single source was David McCullough's The Path Between the Seas, which remains the definitive account of the canal's construction after nearly 50 years. The technical details of lock operation came primarily from Panama Canal Authority documentation, supplemented by engineering literature on hydraulic structures. The 2023 Drought Data and Expansion Project figures came from the authority's annual reports and maritime industry publications. What kept pulling me back into this material was the relationship between the canal's engineering and the terrain it was built in. De Lesseps failed not because he lacked resources, but because he refused to let the terrain tell him what was possible. The Americans succeeded because they listened to what the terrain was offering and designed around it rather than against it. The water staircase is not the obvious solution to crossing a mountain range with a ship. It is the solution the mountain made necessary. And that principle, design for the constraint rather than against it, runs through every element of the canal that has lasted. The miter gate seals tighter under pressure. The gravity culverts need no pumps to fail. The artificial lake controls the river that would otherwise destroy the canal. Each solution turned a problem into a feature. That is what engineering looks like when it works.